अच्छा, आपको स्क्रीन नजर आ रही है आप लोगों को? हम्म। इज द स्क्रीन शेयर्ड? जी, अस्सलाम वालेकुम। ये स्क्रीन आप लोगों को नजर आ रही है?
यस सर, नजर आ रही है।
अच्छा। सो आज के लेक्चर से पहले मैं जो हमारा लेक्चर 9 था, मैं वो जो है ना उसकी कुछ स्लाइड्स आपको दिखाना चाहता हूँ ताकि यू रिमेंबर। कुछ टॉपिक्स हमें चाहिए आज के लेक्चर के साथ जो है ना कनेक्शन बनाने के लिए। सो in that chapter we studied properties of fluid and how it gave rise to friction. In particular, whenever you have relative motion between a fluid and some solid, let's say this is a fluid motion and this is some solid. So if there is relative motion between these two, either the fluid is moving relative to the surface or surface is moving relative to the fluid, तो इसमें ये है कि you will have this shear stress or that is because of viscosity, ठीक है, and that gives rise to fluid friction। ठीक हो गया। अब यहाँ पे हम जो है ना बाकी चीजें I don't want to repeat that, but one thing you need to remember is this। वो बंद कर दे वो वाला, और ये मेंटेनेंस वालों को बता देना कि इसका फायदा तो कोई नहीं है अगर ये इतना इतना शोर कर रहा है तो। ठीक है। Okay, so if you can recall, Reynolds number was a way of quantifying the condition under which the flow is laminar, like smooth laminar flow, or turbulent. Okay, when you have these turbulent and these curls. So if you have this Reynolds number, like in the denominator you have viscosity and the numerator you have density, velocity, distance, length of a body of fluid. So ये number अगर आपको याद होगा, if this is very large you will have most likely turbulent flow, and if this is small, near 1 or less than 1, then you will have laminar flow. So the Reynolds number tells you a balance between inertial forces and viscous forces. If viscous forces dominate, then you will have laminar flow, and if inertial forces dominate, then you will have turbulent flow. Now this thing will be relevant to something more important, and that is the drag force. Okay. So here you can see that there will be relative motion between a solid object like an airplane and the air. Air is also a fluid, so whenever there is relative motion, you will have that fluid friction, and the object moving through the air or through any other fluid will experience what we call the drag force. अब यहाँ पे जो चीज नोट करने वाली है वो ये है कि जो drag force है, it depends on density, it depends on area of exposure, and square of velocity, square of the speed, sorry, and there is this drag coefficient which tells you, okay, the type of fluid and the geometry and area, yeah, geometry other than area. So remember that in general you will have this square of speed. Okay, so you can say that, okay, to cut the long story short, the drag force will be proportional to the square of speed. Now here we discovered that for some simple shapes like spheres, if you have a spherical object moving uh, through a fluid, And if we consider small Reynolds numbers and large Reynolds numbers, yeah. So small का मतलब ये है कि यहाँ पे you are talking about laminar flow, और large का मतलब ये है कि you are talking about turbulent flow. Even if you do not want to use these names, you just say large and small. So it turns out that the drag coefficient itself, remember the formula was that drag force was half rho A mu V squared, okay? Remember, no, it was not mu. Yeah, it was CD V squared. Now this CD itself depends on Reynolds number. And when it depends on Reynolds number, it also depends on velocity as well as density as well as viscosity. And if you see that for small Reynolds numbers, the CD has this particular relationship with Reynolds number. Reynolds number is in the denominator, so you can say that the CD is proportional to 1 over Reynolds number. And because 1 over Reynolds number is proportional to velocity, you can say that CD is also proportional to 1 over velocity. And when you plug that 1 over V dependence, you can say that the force will now depend on velocity. वो square 1 over E के साथ एक V cancel हो जाएगा, and you will have this linear relationship between speed and drag force. ये अब और ये इसकी example है, ठीक है ना, कि the drag force is proportional to velocity. That's interesting. Now this is something which we will use in today's slide. That was just a reminder. But before that, that was a bit of that was a story about the fluid friction and how it arises from viscosity. But you also need to compare it with dry friction. When you have dry friction has a constant value if the object is moving, and if it is at rest, then it will have a value that increases with the applied force until it reaches a maximum value. Okay, so if you in this region you can say that the kinetic friction, or you can also say dynamic friction, you call it kinetic friction or dynamic friction, that if you plot it against velocity, so you will have this constant plot. Okay, we need to distinguish between positive and negative because we know that it will always be opposing velocity. But this is very much different from what we saw in the other slide, where we saw that the drag force was proportional either to the square of the speed in general, and in the special case it was proportional to the speed, especially for low speeds. Now it is very different from dry friction because dry friction remains constant with the speed, and this variation is only a consequence of the sign, which means that it only opposes the velocity. So that brings us to this topic we are going to discuss today, and that is the damping elements. Okay, so so far we have discussed mass or inertia, then we discussed the spring elements and or elastic elements, and now we'll discuss the damping elements. Damping element is used particularly for fluid friction. Okay, so what you need to keep in mind that you have fluid friction arising from shear and viscosity, and shear, is because you imagine, let's say you imagine a piston type thing moving inside a cylinder. Okay, and if that cylinder has fluid in it and this piston has holes in it और ये उसका कट आउट सेक्शन है, तो ये जो होल्स हैं in holes ke through, because the fluid can move in and out. So whenever the piston moves one way or another, the fluid motion relative to these valves, yeah, will give rise to shear and viscosity. In other words, you have a resisting force. Okay, जो हमारे पास drag force था, वो हम इस context में उसको resistance force कहेंगे, and because it's in translational, we call it the translational damper. Example आपने देखा होगा, door closer आपने देखा होगा कि if you have a door which you open and close, and let's say this is the door frame, so you must have seen a cylinder type thing, and inside this cylinder you have a spring. Basically ये cut out section है, आपको spring नजर आएगा. Spring, we need spring because when we open the door, we want the door to close automatically, and that requires a spring. Okay, the spring stores energy, restoring force. When you leave it, it comes back. But that's not the only thing you see in a in a shock absorber or door closer. We also want this this setup to resist high speed motion, okay, or speed variations. So because that damping force depends on velocity or velocity squared, so the faster it tries to move, the more the drag force, and that's how it will dampen. Yeah, that's why we call it a damping element. Damp का मतलब ये है कि if there are oscillations, yeah, so आपने देखा होगा सर्किट में भी आपने वो classification देखी थी ना, undamped, underdamped, or overdamped, or critically damped. So basically, if the door oscillates like that with time, this will be undamped. And if it oscillates like this, yeah, then this the drop of amplitude is what we call the damping. But because it still oscillates, we call it underdamped. And if it never oscillates at all, then we call it overdamped. So तीनों में damping is the element. Damping, the level of damping tells you whether it's over relative to the other features. So the one example you see in this slide is the door closer. The other example is shock absorber. You must have seen in automotives, and the next slide will have an example of that. Okay, so the shock absorber can look like that, or it can look like that. So you can see that you have this wheel motion, and if it hits a bump, then this element with a cylinder and fluid and some valves, piston type arrangement, and the cutout section can be seen here, is that okay, you have some fluid through which the piston moves one way or the other, and these two valves are spring loaded, yeah, and the diameters can differ, the spring constants can differ in such a way that if you plot the damping force against the speed, so it is possible that in one direction, which you can say the rebound, and the other direction compress. So in one direction you can have a large force, a large damping force, and in the other you have a small damping force. Now how can this benefit? So you can design these two sides, like this spring and this diameter, and this spring and this diameter, in such a way that when you hit a bump, that will actually compress the tire. So that in that direction you would like small force. The compression, you would like the compression to be small, because you don't want that force to transmit to the passengers. But when this spring comes back, that can be large, okay, because you want to save other parts of the vehicle from this vibration. But that is too much detail. Maybe you don't need that much detail, okay. The critical message which you must learn from this plot is to compare it with that other plot of kinetic friction, solid friction, when you had dry friction. Dry friction में क्या था? It was a flat line. It was a flat line. Here you have some other type of dependence, और ये याद होगा इसकी वजह ये है कि the drag force is proportional either to v squared or to v. ठीक है ना? So dry की case में the friction force only depends on the sign of velocity, okay, plus minus, not on the magnitude. Another thing which you need to notice in this slide is the rotary or torsional dampers. So, okay, so damping is not just in translation. Here you see a body of liquid or fluid which experiences relative motion with some other rotating body like a wheel or any rotating body. So because of these holes through which the fluid can pass and rotate, you will have a resisting torque. So you can have damping force or damping torque depending on whether you have translation or rotation. So remember, in shock absorbers the piston is spring loaded, and because of the fluid you definitely will have damping and velocity dependence. So these are the keywords which you need to remember. Okay, this setup you will see in aircrafts, especially for landing. Okay, this brings us to this simplification now. So if you recall, for springs we had real springs which could have mass भी इसमें था, inertia भी होता था, but then we had the idea of ideal spring. ठीक है, ideal spring में ये है कि हम mass को कहीं और represent कर लेते थे, and the ideal spring had no mass. Same is the case with ideal damping element. The real damping elements which you saw in these figures, they do have mass, but the ideal damping element will be massless, which means that the mass will be represented somewhere else in some other rigid body, to simplify the models. Okay. अब इसमें जो चीज आपने नोट करनी है कि ट्रांसलेशनल उसका सिंबल ये होगा डैम्पिंग का, और रोटेशनल का ये होगा. ठीक है, और रोटेशनल फिर दो टाइप्स हैं. If this is the general one, the general rotational damping, but if that damping comes from some bearing, remember you have a shaft and that shaft is actually rotating inside a bearing, तो bearing का फिर symbol ये होता है. ठीक है, आपने नोट करना है. But that is ideal is one simplification. Yeah, so when you go from real damper to ideal damper, you set mass to 0. Okay, so you assume that there is no mass. But ideal damper can be linear, it can be non-linear. So if we have linear damping, and the example, I just repeat this figure, that for low Reynolds numbers or for low velocities, yeah, the coefficient of drag can have a relationship or dependence on the speed in such a way that that square relationship reduces to a linear relationship. In that case we will call it linear damping. So linear damping may the constant of proportionality is called the damping coefficient in translation, and in rotation it's called torsional damping coefficient. तो यहाँ पे हम CT नीचे लिखेंगे, यहाँ पे सिर्फ C लिखेंगे. वैसे बहुत ज़्यादा complicated है, लेकिन for certain special types like the piston type which I just showed previously, yeah, these piston types, for these you can derive, and we will not derive these relationships, the damping coefficient to have this formula. Okay, it's very easy to use the formula because it has this 8 in it. Pi, then mu is the viscosity, L is the length of the piston and cylinder, D is the diameter of the cylinder, small d is the diameter of the piston, and you know square and all these things. For torsional damping coefficient, you again have pi. D is for the diameter of the bearing. This is for bearing, okay? So not all torsional damping coefficient, but for general bearing, these general bearings. L is the length, of course. D is the diameter. Mu is the viscosity of the fluid, and epsilon is the thickness of the layer. क्योंकि बियरिंग जो भी आपने, अगर आपने बियरिंग कहीं देखी हो, शाफ्ट जिसके अंदर रोटेट करता है, वहां पे you do need lubrication, okay? Lubrication के बगैर you will have a lot of wear and tear, and it can actually break because of heat. So lubrication का जो film की जो thickness है वो epsilon है. And if you know all these parameters, you use this formula or this formula for translation. This is for translational, this is for rotational or torsional. One other thing you need to remember when you read these diagrams is, just like if you recall the spring, when we had spring, the two ends had displacements, and only when there is relative displacements, if these two are equal, then there is no restoring force. But if they are unequal, and if let's say x1 is greater than x2, then you assume this end to be moving forward relative to this end, which means that on this side of the spring, the restoring force will be opposing. And once you identify this force, the other force will automatically be opposite. So that same logic can be applied to these diagrams. Like if I go with this one, I have this end of the damper and this end of the damper. And remember, this end of the damper is corresponding to the piston moving, and this end corresponds to the damping. To the cylinder, piston in the cylinder. And overall, this is the damping element. So if you assume there must be a difference of speed or difference of velocity between those two ends for the force to exist, क्योंकि ये जो v है ये relative velocity है between these two, okay? So if you assume v1 to be greater than v2, just look at this diagram. What you are asserting by that inequality, that relative to this side, which is the piston, moves towards the right, and when it moves towards the right, the opposing or resisting force will be in the opposite direction, and c times this difference will be the force, okay? Don't use the word restoring here, okay? Because restoring is the word used for springs. Here you just say friction force or drag force or resisting force, whichever one you like, okay? On the other hand, if you assume V1 to be less than V2, then instead of this, you will have V2 minus V1. And there you mean that this body, because this speed is smaller, this part is trailing behind that part. Relative to that, it is trailing. When it is trailing, the force will be opposite, okay? So the friction force or the drag force or the damping force will always be opposite to the relative velocity. Our relative velocity, depending on whether V1 is greater or whether V2 is greater, the arrow will differ, and the arrow always needs to be opposite the relative velocity. Same goes with torsional springs, that if one end has angular velocity omega1 and if the other end has angular velocity omega2, if omega1 is assumed to be greater than omega2, the opposing torque or resisting torque will be opposite to omega, okay? और ये चीज आपने प्लस माइनस में नहीं शो करनी है, आपने एरो में शो करना है. The arrow must indicate that opposition, okay? ताकि आपको माइनस साइन अलग से ना लिखना पड़े. देखो ना, because this arrow is opposite the arrow of v1 minus v2, so you don't need the minus sign there. So same applies to the resisting torque. Remember यहाँ पे अगर हम C यूज कर रहे हैं तो यहाँ पे हम CT यूज कर रहे हैं, ठीक है, and we assume linear damping, ठीक है। अच्छा, ये यहाँ पे linear damping, या तो उसको आप नाम बता दें कि linear damping है, या आप ये फार्मूला बता दें, ये वाला या ये वाला। इसके लिए वैसे इसके लिए जो फार्मूला होगा ना, इसके लिए instead of force you will have torque. That resisting torque will be equal to the drag coefficient, the torsional damping coefficient, and this will multiply the relative angular velocity. Okay. अब या तो linear लिखा हो या फार्मूला बताया हो, ना भी बताया हो ना, if I have a symbol, if I have schematic symbol like that, and schematic symbol पे अगर मैंने ये लिख दिया, schematic symbol पे मैंने ये C की वैल्यू लिख दी, या यहाँ पे CT की वैल्यू लिख दी, so ये this assume that you have linear damping, ठीक है ना, क्योंकि अदरवाइज आप ये वैल्यू नहीं लिख सकते, इस वैल्यू का मतलब ये linear है, ठीक है। फॉर एग्जाम्पल आपने रेजिस्टर यहाँ पे लिख दिया सिंबल और यहाँ पे लिख दिया 3 ohms, अब इसका मतलब ये है कि यू आर अज्यूमिंग ए लिनियर रेजिस्टर और ओमिक रेजिस्टर। अगर ये नॉन ओमिक है, in which case you want to say that it does not follow the straight line between current and voltage, तो फिर आप ये यहाँ पे ये वैल्यू लिख ही नहीं सकते, ठीक है, आप वैल्यू नहीं लिख सकते। वैल्यू लिखने का मतलब ये है कि यू assume linearity, ठीक है। So the punchline so far for these damping elements is this new relationship, okay, where the damping force is some constant which we call the damping coefficient times the velocity. So far we only had spring force, and that spring force was K times X, or the torsional, for the torsional spring it was KT omega. And just like this X was a relative displacement, this omega, sorry, ये spring में ये omega नहीं होगा, theta होगा, sorry, relative deflection, relative displacement, तो damping में भी ये relative velocity, relative angular velocity and so on, ठीक है। So the essential equation to pick from this slide is this one, and the analogous for the torque, which is CT omega. अगर आपको ये दो इक्वेशन समझ आ गई और इसकी मीनिंग, so you can now solve these examples which we are not starting. The first example which involves damping elements is 4.4.1, and you see that you are asked to derive the equations of motion. अच्छा, इस तरह के examples में solve का भी आता है कि solve those equations, but we are not solving anything in this course. So मैं ignore कर देता हूँ, we are only picking, writing down the equations. So the block sliding, ये sliding block है, wheels कोई नहीं है, on an inclined lubricated surface. अब यहाँ पे surface dry नहीं है, lubricated है। अगर dry होता तो यहाँ पे solid वो dry friction होता, dry friction। यहाँ पे चूंकि lubricated है, you will have fluid friction or damping element. Assume the damping force to be linear. So now if you want to draw the free body diagram, as usual, this mg can be decomposed into two elements, two components. This component will actually balance the normal force, and that will not cause to any motion because there is no jumping. But along the incline, this force, the component of gravitational force, will be balanced by the damping force, which will always be opposite to the relative velocity between this body and the surface. Okay. एक तरीका तो ये है कि इसने ये बेसिकली इसको मैं, if I want to go to the symbol, एक तरीका तो ये है कि आप यहाँ पे जो है ना ये ये डैम्पिंग एलिमेंट इस तरह का इसका फोर्स शो कर दें, but it is also a good idea to just represent the mass with a damping. Okay, you can represent this with a damping element और यहाँ पे लिख दें C. ठीक है, so this is the same as this. आप इसके लिए भी इक्वेशन लिखेंगे तो free body diagram will look like that. Now if we take this free body diagram and if you want to write the equation of motion, you just apply the Newton's law. Newton law में हम लेफ्ट साइड पे क्या करते हैं, velocity dot times mass, और राइट साइड पे क्या है, total force. The force in the direction of V is mg sin theta, and the force in the direction opposite to V is c times V, और इसके साथ हमने माइनस साइन लगाना है, देखो ना, प्लस माइनस, and that is how you arrive at the damping force. So in the equation of motion. Okay, if I rewrite this equation in a form, let's take this minus CV to the other side, and it will be plus CV, and the right hand side will be mg sine of theta, and let's call this mg sine of theta f. So now you have mv dot plus CV equals f, and if you look at this equation, okay, if you look at this equation, and if you compare this equation with an equation for an RL circuit, okay, let's say you have a resistor and you have an inductor, you have some voltage V, don't confuse this V with velocity, okay, and maybe I should write E for that purpose, and then let's say this is current. So if you write down the equation for that, it will be R times I plus L times the derivative of the current equals the voltage E. If you compare these two equations, you have some interesting analogy that if you compare force with the voltage and velocity with current, you can see that the damping constant C is analogous to resistance and the mass M is analogous to inductor. That is very interesting. That is why a resistor in electrical circuits is always associated with damping. ठीक है ना, damping. क्योंकि C is damping and resistor is damping. ये बात समझ आ गई? Let's move on to the next example. So the figure on the right, now this is an example of torsional damping or rotary damping. The figure on the right illustrates a wheel axle system. So you have a wheel here. You have a wheel here, and there is this axle, and that is actually supported by two sets of bearings. You have one bearing here and one bearing there. ठीक है, दोनों का अपना CT है. CT लिखने का मतलब ये है कि you are assuming linear damping. ठीक है, linear damping ना होती तो आप यहाँ पे CT की वैल्यू कभी ना लिखते. Now each bearing set has a torsional damping CT. इसका मतलब ये है कि linear है. The torque T is applied by a motor. तो यहाँ पे torque T is supplied by the motor. Now the force F is the friction. ये जो force है ये friction force है, ठीक है, due to the road surface. Derive an equation of motion. अब equation of motion के लिए ज़ाहिर बात है we need to have a free body diagram for this wheel. इस wheel को अपने साइड से देखना है तो इसका inertia I होगा. अब मसला ये है कि इसका इस डायग्राम में इसका inertia IW है. So IW is inertia of the wheel, IS is the inertia of the one shaft, and IS is the inertia of the other shaft. So if I can simply add these two inertias to that inertia IW and the overall inertia I, or I can say effective inertia, but I don't need to, I can simply say I is the overall inertia. इस डायग्राम में जो आपको I नजर आ रहा है, ये जो आपको I नजर आ रहा है, ठीक है, ये this is the overall inertia, ठीक है. अब इसकी आप एंगुलर वेलोसिटी है, ये हम इसलिए भी कर सकते हैं ना कि इस शाफ्ट के सारे अगर रिजिड बॉडीज हैं तो इन सबकी एक ही वेलोसिटी है, ठीक है ना. सो दैट्स व्हाई वी कैन जस्ट यूज अ सिंगल रिजिड बॉडी. ये उसका फोर्स है रिएक्शन फ्रिक्शन का इस एंड पे सरफेस के साथ, दिस इज सरफेस. T applied torque है, and because there are two bearings, so each one of them will offer a resisting torque which is Ct times omega. और अब हम लिख सकते हैं equations of motion, ठीक है. So let's write down the equations of motion. Equation of motion हम कैसे लिखेंगे इस बॉडी के लिए? We just write down the moment equation, basically omega dot times I, and by I means this I, okay, this is the I. So उसमें ultimately आपने ये plug करना है इधर. And if you look at omega as your reference direction, T and omega are in the same sense, so T is positive. Now F times R, F चूंकि इस साइड पे है और R ये है, तो F times R का जो torque होगा, that is also in the direction of T, because they are both clockwise, okay. अब clockwise आप ये ना कहें कि clockwise negative है, we have to follow omega. As long as a term is in the direction of omega, that will be positive. But this damping torque Ct omega for both the bearings, that is opposing omega, okay, so that is minus omega, and that is your equation of motion. So you don't need to actually complicate things. Okay, the next example is interesting because it has all the three elements you studied so far. It has mass, it has damping, and it has spring. अभी तक हमारे जितने भी एग्जांपल्स थे उसमें या मास और स्प्रिंग कंबाइन होता था, और अभी थोड़ी देर पहले जो आपने एग्जांपल देखी है उसमें यू कंबाइंड मास विद डैम्पिंग, ठीक है. अब यहाँ पे हमारे पास पहला एग्जांपल आ रहा है जिसमें आपके पास तीनों एलिमेंट्स हैं, एंड दिस मेक्स सेंस क्योंकि रियल सिस्टम्स में जो आपके पास फिजिकल सिस्टम है उसका मास भी होगा, उसमें ऑफ कोर्स फ्रिक्शन भी होगा, डैम्पिंग भी होगी, और उसमें स्प्रिंग स्टिफनेस भी होगी. सो यू कैन नॉट इग्नोर ऑल दीज प्रॉपर्टीज. सो दिस इज मोर रियलिस्टिक. एंड F इज द एक्सटर्नल फोर्स, ओके. एक्सटर्नल फोर्स यहाँ पे क्या है? F है. So if you take this as your rigid body, ये external force F आ गया, and of course when you want to stretch this spring downwards, Kx is the restoring force, and when you want to move the piston, no, not the piston, the cylinder, downward relative to the piston, because the damping force is opposite the relative velocity. Relative velocity यहाँ पे क्या है? X dot. So x dot times c will be the damping force. अब आपके पास एक रिस्टोरिंग फोर्स है ऑफ द स्प्रिंग, एक है डैम्पिंग फोर्स और रेजिस्टिंग फोर्स और ड्रैग फोर्स और फ्रिक्शन फोर्स, जो भी आप इसको कह दें. ड्राई फ्रिक्शन के साथ कंफ्यूज ना करें इसको, फ्लूइड फ्रिक्शन. तो दो फोर्सेस, टू फोर्सेस आर opposite x and one force is in the same direction as x. So now we can actually apply Newton's law. Newton's law में हम क्या करते हैं? For rigid body we write m times x double dot, and you have applied force F, प्लस है, और जो बाकी फोर्सेज है k टाइम्स x भी माइनस होगा और c टाइम्स x डॉट भी माइनस होगा, क्योंकि रिस्टोरिंग फोर्स भी अपोजिट है और डैम्पिंग फोर्स भी अपोजिट है. Now if you look at this and if you compare this with the electrical system, so this can be seen analogous to inductance. This can be analogous to voltage. This K, this C can be analogous to resistance, and this K, if you look carefully, this is analogous. अगर आपने वो equation देख लिया ना कैपेसिटर RLC सर्किट का, RLC, तो वहां पे पता चलेगा कि this K is analogous not to C but to 1 over C. ठीक है, and this makes sense क्योंकि K is the stiffness, and stiffness actually is in the sense of opposition. तो इसका जो 1 over K है that will be compliance. तो compliance actually represent flexibility. So capacitance should be, capacitance का मतलब ये है कि आप उसमें ज़्यादा से ज़्यादा चार्ज स्टोर कर सकते हैं. So capacitance should be analogous to flexibility, and flexibility is compliance, which is 1 over stiffness. So that's why K is analogous to 1 over C and not to C. ये दोनों का sense different है. ठीक हो गया? Now I need to ask you something here. Let me just declutter everything, write down the equation again. Now if I start with this equation, okay, and if I ask you that does this represent simple harmonic motion, तो आपका आंसर क्या होगा बताएं? Try to recall how do you check if an equation represents simple harmonic motion or not. उसके लिए क्या condition है? Let me help you by starting with, उसमें क्या था कि acceleration must be proportional to, there was a minus sign because acceleration must be opposite, और यहाँ पे क्या था? If you remember, displacement. अब यहाँ पर displacement क्या है? x है. Acceleration क्या है? x double dot. Now this force is not a problem क्योंकि ये तो external force है. That is not a property of the system. लेकिन x is a property of the system. तो अब जो x dot term है, that is causing the problem. क्योंकि simple harmonic motion में यहाँ पे displacement है, velocity नहीं है. There is no velocity, which means that this is not simple harmonic motion. If you want to convert this to simple harmonic motion, you must set c to 0. अब आपको समझ आइए कि c को हम डैम्पिंग क्यों कहते हैं, क्योंकि डैम्पिंग आपको याद है मैंने कहा था कि अगर ये ऑसिलेशन कम नहीं हो रही है, if it keeps oscillating, that's what we mean by simple harmonic motion. So simple harmonic motion is just another name for undamped, don't confuse it with underdamped, undamped oscillations. अगर oscillation pure है, undamped है, उसका constant amplitude, तो उसको हम क्या कहेंगे? Simple harmonic motion. उसके लिए जरूरी है कि डैम्पिंग 0 हो. तो आपको समझ आ भी गई होगी इसको डैम्पिंग. Why does C represent damping? Because it is the value of C which prevents. अब अगर ये C non-zero हो गया तो फिर आपके पास ये जो oscillation है ये फिर ऐसे नहीं हो सकती. The oscillation has to be decaying. ठीक है ना, वो जो decay आप यूज करते रहे हैं सर्किट में, that decay is a consequence of the damping element, जो कि इलेक्ट्रिकल सर्किट में रेजिस्टेंस था, और यहाँ पे क्या होगा? यहाँ पे वो C होगा. ओके अब यहाँ पे अभी तक हमने जितने भी एग्जांपल्स देखे हैं ना, यहाँ पे आप एक चीज नोट करें बहुत जरूरी कि and this is something which you have done and you must have seen in circuits as well. Let's say मेरे पास एक सर्किट इस तरह का सर्किट है, ठीक है। अब आप नोट करें कि इस लाइन को आप जितना भी लेंथी करें ना, सो अब चाहे ये पॉइंट ले ले, इन सारे पॉइंट्स का you associate the same node because they all have the same potential. Similarly, all these points अब यहाँ पे ले ले, यहाँ पे ले ले, यहाँ पे ले ले, यहाँ पे ले ले, they all have the same potential. So ये दूसरा नोड हो गया. Same is the case with the displacements and velocities. ठीक है। अब ये रिजिड बॉडी है आपके पास, तो अब इस रिजिड बॉडी पे आप ये पॉइंट ले ले, ये 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 ले ले, या ये लाइन इधर तक। इसका मतलब ये है कि यहाँ से यहाँ तक ये जितना भी रीजन है ना, इसमें m इंक्लूड कर दे, they all are represented by a single displacement. So they all can be represented by a single point mass. Okay. Similarly, rigid body, ठीक है, K is not a rigid body. तो K के बारे में आप ये नहीं कह सकते कि ये पॉइंट और ये पॉइंट और ये पॉइंट इन सब का नहीं। K is a flexible body और deformable body, तो उसके हर पॉइंट की डिस्प्लेसमेंट जो है ना वो इंडिपेंडेंट होगी, डिफरेंट होगी। हम बात कर रहे हैं रिजिड बॉडी की, ठीक है। सो इसका मतलब ये है कि इस पूरे डायग्राम में हमारे पास बेसिकली दो पॉइंट्स हैं। एक इन सब के लिए you need one point x, और बाकी ये जो आपका सपोर्ट है और ये सारे पॉइंट्स इनके लिए because you take that 0, that's why ideally तो ये होना चाहिए था कि ये x1 होता और ये x2 होता, and then this x is x1 minus x2, लेकिन हम उतने कॉम्प्लिकेशन में नहीं जाते, हम इसको 0 कह देते हैं and this becomes our x. Okay, but that is how you identify the different nodes. So आप इसको भी नोट कह सकते हैं, सर्किट में भी आप नोट कर। अब यहाँ पे थोड़ा सा ये प्रॉब्लम थोड़ा सा डिफरेंट है, क्योंकि if you want to write the equation of motion for this system, this mass इसके लिए you need one variable x, ठीक है, क्योंकि there all these map to a single point. ये समझ में आ गई बात। Similarly, this support and all this stuff also needs one displacement, और वो हमारा 0 है, रेफरेंस 0 है, ठीक है, तो उसको हमने लेबल करने की जरूरत ही नहीं है। लेकिन ये जो पॉइंट है K1 और C के दरमियान, ये जो एरिया है पूरा, आप इसको ना K के साथ मिक्स कर सकते, क्योंकि all these points are different, all these points are different, और इसको इसके दूसरे एंड के साथ भी नहीं कर सकते। It is a displacement in its own right, इसकी अपनी वेलोसिटी होगी, अपनी डिस्प्लेसमेंट होगी, ठीक है। So this point in the middle between K1 and C, this will have its own velocity y dot and its own displacement y, even though this has 0 mass. तो अब यहाँ पे जरूरी ये है कि शायद ये मैं पहले बता चुका हूं या नहीं, जो रिजिड बॉडी है या पॉइंट पार्टिकल है, बिकॉज पॉइंट पार्टिकल इज अ स्पेशल केस ऑफ रिजिड बॉडी, पॉइंट पार्टिकल, इसके लिए जरूरी नहीं है कि मास नॉन जीरो हो। मास कैन बी जीरो because the mathematical definition of rigid body and point is that it should have a dedicated independent velocity and displacement. आपने अक्सर देखा होगा कि डायग्राम में आपके पास यहाँ पे एक इस तरह पेंडुलम में ये रॉड होता है, ठीक है, और ये तो इस पूरे रॉड को हम रिजिड बॉडी के तौर पे मॉडल कर सकते हैं इवन इफ इट हैज जीरो मास। तो रिजिड बॉडी के लिए मास का नॉन जीरो होना जरूरी नहीं है। What is required is that it must have an independent position and velocity. Because the point between K1 and K and C has its independent displacement and independent velocity, we will model this point as a rigid body. Okay, even if the mass is zero. ये बहुत जरूरी है ये point. ये इसलिए है कि इसके लिए हम इक्वेशन लिख सकें। आप रिजिड बॉडी की ही इक्वेशन लिखेंगे, ठीक है। अब आप कह सकते हैं कि नहीं, मैं यहाँ पे k1 उठा लेता हूँ यहाँ से, इसकी कांस्टेंट ये है और मैं इसके लिए फॉर एग्जांपल लिख देता हूँ कि फोर्स इज इक्वल टू kx। अब ये इक्वेशन ऑफ मोशन नहीं है, दिस इज नॉट एन इक्वेशन ऑफ मोशन। इक्वेशन ऑफ मोशन में डॉट होता है, डेरिवेटिव्स होते हैं, इसमें कोई डेरिवेटिव नहीं है, ठीक है। इक्वेशन ऑफ मोशन आप सिर्फ रिजिड बॉडी के लिए ले सकते हैं। आप इक्वेशन ऑफ मोशन k1 के लिए नहीं लिखेंगे, k2 के लिए नहीं लिखेंगे, c के लिए नहीं लिखेंगे, आप लिखेंगे मास के लिए और इस पॉइंट के लिए। सो यू हैव वन फ्री बॉडी डायग्राम फॉर द मास, one free body diagram for that point, two particles, one particle has mass, the other particle is massless. अब इसके लिए हम, you can identify all the forces, applied force, opposing forces. Yeah, this is action reaction. देखो ये और ये हमेशा different होंगे. And if I now want to write the equations, I can write the equation of motion for this body now. I can start with that body, and that is m का वो क्या है, displacement x. So I can start with x dot, x double dot. One force is F, which is plus because it's in the same direction as m, x. Then you have minus k2x. Okay. And minus c x dot minus y dot. And remember, whenever I write x dot minus y dot, I assume x dot to be greater than y dot, so that this is positive, okay? And that will dictate the arrow, because if you assume x dot to be greater than y dot, you are imagining this end to be moving faster relative to that end, and the opposition will always be upward. Whenever one end is faster relative to the other end will try to pull it to justify calling it a reaction force. So हमने ये भी कर दिया. Now we can try to write the equation of motion for the second rigid body, which is massless. This one. उसके लिए क्या है, लेफ्ट साइड पे जीरो होगा क्योंकि जीरो टाइम्स एवरीथिंग इज जीरो. बेसिकली यहाँ पे जीरो इज द मास एंड यू विल से y double dot. So 0 times y double dot is 0, and the net force is y की डायरेक्शन में c times x dot minus y is in the direction of y, and k1 times y is against y, so that's plus, this is minus. And you can now add these equations. If you add these equations, on the left hand side you will have mx double dot, on the right hand side you have f minus k1y minus k2x minus c. नहीं, ये तो कैंसिल हो जाएगा ना, ये दोनों कैंसिल हो जाएंगे, प्लस 4. ये कैंसिल हो जाएंगे. So that is your equation of motion, ठीक है. If you have any questions, you can ask now. There is one problem with this last equation which we need to think about. Although this equation is technically okay, but there is one problem, and that is that you have one equation, and how many unknowns? Two unknowns, y and x. If you assume f, because f आपने देना है outside word ने, you assume that you know f. तो अगर आपको f का नहीं पता, अब आपके पास एक इक्वेशन है जिसमें y भी अननोन है, x भी अननोन है, तो इट्स अ बिट ऑफ अ प्रॉब्लम. तो इसको हल करने का एक तरीका तो ये है कि हाउ अबाउट differentiating this equation. Let's say differentiate this equation. Differentiate each term with respect to time. तो लेफ्ट साइड पे क्या बन जाएगा? You will have m x triple dot. Here you will have f dot. Here you will have k1 y dot. Okay. And here you will have k2 x dot. अब आप कह सकते हैं कि यार हमने क्या तीर मार लिया, but now you can do something. If you, because you know that left hand side is 0, from this equation you can actually express y dot and y. मेरे ख्याल में इसको एलिमिनेट ऐसे नहीं कर सकते हम. I'm just wondering how can we eliminate y from this. वह मतलब जो बुक में जिस तरह किया है मैं उस तरफ जाना नहीं चाहता क्योंकि वो बहुत आसान है. वो क्या करते हैं, वो लेप्लास ट्रांसफॉर्म दे लेते हैं दोनों साइड पे. तो लेप्लास में फिर डेरिवेटिव इज, हाँ सॉरी कुछ कहना चाहते हैं? If you replace the derivative with s, you have these algebraic equations. और algebraic में फिर आपके पास y डॉट और y में फर्क नहीं रहता क्योंकि इस y में सिर्फ s टाइम्स y लिखते हैं, ये y लिखते हैं. तो आप you can solve this equation for y in terms of x और उसमें and then you plug it and then you get rid of y. अब यहाँ पे चूंकि उस तरह हम Laplace डोमेन में नहीं है, तो we somehow need some more algebra to get rid of y. And I'm not sure whether this is recommended क्योंकि अगर ये इतना आसान होता तो Laplace transform की तरफ लोग ना जाते. So let me think about this. If I, क्योंकि Laplace से करना तो कोई वो नहीं है, algebraic में आपको पता है कि you can get rid of y. ठीक है, मैं इसको लेके देता हूँ, आपको समझ आ जाएगी कि मैं क्या कहना चाहता हूँ. Let's say मैं ये इक्वेशन Laplace डोमेन में लिखना चाहता हूँ. It will be 0 c और डॉट का मतलब s है, तो it will be s times x minus y minus k1 times y. और यहाँ पे ना from this equation you can write an expression for y in terms of x, and when you plug it there in the other equation Laplace transform, you get rid of y automatically. टाइम डोमेन में थोड़ा सा ये कॉम्प्लिकेटेड है. So let me see if I can come up with a way to get rid of this y and y dot without using Laplace transform. ठीक है, अगर मुझे कोई मिल गया ठीक है कर लूंगा, लेकिन otherwise आप इग्नोर करें. Our purpose of solving this example was just to write the equation of motion. Okay, बुक में उसने उसको Laplace transform को भी सॉल्व किया है, कैरेक्टरिस्टिक इक्वेशन भी लिखा है. That is not the goal of this course. ठीक है, if you have questions you can ask now.